All right, I believe we've reached a good number. Many thanks for everyone for joining. It is a pleasure to have you all for this closing event for the C⁴U project. I'd like to start straight into some context onto what we're going to discuss today. So unfortunately, our project coordinator, Harun, is having some trouble joining us, but he will be with us shortly to introduce the project and letting you know a bit more into what we've done for the past 5 years and what we would like to show you today. But we will start shortly with a presentation on the readiness frameworks for CCUS adoption in Europe that we have developed throughout the C⁴U project. This will be presented by our colleagues Vincent de Gouyer by Radboud University and Hannah Galbraith-Olive from ERM. Then we will continue with a panel discussion with some very esteemed guests on their perspectives on the current landscape of CCS in Europe from different points of view in the field. And then we will go on into a series of presentations into the CCTUS Research and Innovation that has been developed by the C⁴U project. This includes the displace and castle capture technologies, which have been the main flagships of this project, as well as other technologies that have been developed throughout this time, including the CWAX technology and our research on tools and other findings for the design and operation of CO2 transport for CCS. At the end of each session, after the panel and after the technical presentations, we will have a brief Q&A session where you will be able to post our questions. So please remember at any point during the event to add your questions onto the chat, and we will do our best to bring them up and put this conversation forward. So I'd like to maybe give it a head start now and give the word to Hannah Galbraith-Olive and Vincent de Gouyer to start the presentation on the research.
I also see that we have Harun in the meeting in the meanwhile. Do you want to give him the floor first?
Oh, I see.
Hi.
Perhaps the technical difficulties have done. Harun, are you with us?
Yes, I'm here. Can you hear me?
Oh, absolutely fantastic. Yes, we can hear you just fine.
I'm so sorry about this. Some issues with the. Can you hear me now?
Oh.
Yes, I'm here.
Yes, we can hear you just fine. Many thanks, Harun.
My sincere apologies to everyone about the this technical issue. I hope to catch up very quickly with. So Ines, have we had the introduction about the C⁴U project yet?
So you arrived just in time. I've just gone through the agenda and it's over to you to introduce the project.
Right, let's go. Okay, this first slide. So my name is Professor Harun Mahgerefte. I'm the coordinator of the C⁴U project. Basically the project, this is I think the second slide, isn't it, Ines? That's it, right. So the project started in 1st of April 2022, and we've got another 2 weeks to its conclusion, which is 31st of March, and it's focused on the capture of CO2 from the iron and steel industry. So if you could move on to the next slide, please, just to set the scene and the challenge. Basically, the iron and steel industry is the largest energy-consuming manufacturing sector in the world, with average specific emissions of about 1.83 tons of CO2 per ton of steel produced. So approximately for every ton of the steel that is produced, you produce 2 tons of CO2, which is absolute when you take account of all the huge amount of steel which is produced worldwide. It's an enormous amount of CO2. And in general, if we consider all the industrial emitters, the steel industry accounts for 8% of the total industrial emissions of CO2. So the capturing of the CO2 is obviously very important in this sector, and because of the nature of the CO2 which is emitted and the huge amounts which is being emitted and the urgency, we really need a portfolio of different capture technologies that need to be developed and tested so that we can basically tackle this huge problem. And of course, reducing costs and energy consumptions and overcoming social economic barriers are a prime factor governing the success of this kind of technologies. So if you could move on to the next slide, please. So this is the C⁴U project in a nutshell. It is a holistic project enveloping several disciplines, starting from the technology development, two of these capture technologies to TRL7 by developing two pilot technologies, separate principles, but both operating on the capture of CO2 using solids. The techno-economic assessment of scaling up, what it takes to scale up these technologies from the TRL7 stage that we've already reached to TRL9, and what the efficiencies and the costs will be. We have focused particularly on industrial clusters primarily. So the first step in that is to integrate our capture technology in the steel industry. We have two capture plants in one pilot plants that we developed. One is in Spain and the other one in Belgium. ArcelorMittal plants, both of them. And of course, societal readiness, because as I said, one of our main focus is industrial clusters. This is the trend in order to tackle global warming, and also the fact that there are many industries in close proximities to one another. The most efficient way of dealing with this issue is in the context of industrial clusters and integrating our technologies so that they are compatible with industrial clusters. Business models, of course, if you capture CO2, it's going to cost money. So you need appropriate business models to entice industry and private investment. Societal acceptance is also a key factor. So as you can see, we are really dealing with a multi-aspect challenge when it comes to the steel industry. The two technologies that we are going to focus on during this commercialization event is the displaced and the cathode technologies that we've developed to TRL7. Next stage is to take into TRL9. There are, of course, also other outputs which have significant commercial potential, as in the C⁴U project that we will cover. These are the development of multi-source flow models for CO2 pipeline transportation, and also business models, as well as, of course, societal readiness and what we've done in order to bring society and the narratives that are needed to bring society on board. So if you could move to the next slide, please. What's special about the steel industry is the myriad of different emission sources that come from different parts of the steel plant, which is quite unique when it comes to the steel industry. Not only we have several sources of CO2 from blast furnace and gas and oxy fuel, all sorts of places from the CO2, from the steel plant that CO2 is emitted. There are different flow rates and different temperatures, different pressures, and different compositions. So this already sets a very significant challenge for capture technology, which has the robustness and the efficiency to deal with all these different sources of emissions. So what is unique about the C⁴U project and the technologies that we developed together, the two technologies that we have developed can handle up to 90% of the CO2 emissions, and overcoming the traditional issues with the other capture technologies such as solvent degradation. I won't say more, you'll hear more about those later. So final slide is how the C⁴U project comes into play. We have in total 8 work packages. The first 6 work packages deal with the fundamental elements of the C⁴U project, encompassing the development of the capture technologies, development of business models, and long-term societal readiness. Of course, important aspects are dissemination, communication, public engagement. This is why we are here today speaking to you, disseminating and communicating in order for ultimate commercial exploitation. And it's a large project, so managing it has been quite a challenge, with 22 partners from 11 countries across Europe, including China, Canada, and the USA. So my apologies again for my late start. So we move on to the next item of the agenda, please. We could go back to the agenda, Ines, and I introduce we have the societal readiness framework for the CCTUS adaptation in Europe. So I introduce our first speaker, Vincent Digueur, and also Hannah Gavirit Olive to talk about their work in this area. Over to you, Vincent.
Thank you very much, Arun. Yeah, a very large and complex project indeed. And I think a unique characteristic of this project is that it has these different levels involved. So it has the level of the technologies, but also the technologies implemented in a plant, the plant in an industrial cluster, and that industrial cluster in a society and a broader policy landscape. My name is Vincent de Gooiert. I'm at Radboud University. I'm the leader of Work Package 5 on societal readiness, and I'm here to talk to you today about this higher level in this project on societal readiness. And I hope that it also helps to set the stage later for the other parts of the presentation focused on the other levels, on the industrial cluster, plant, and technology level. I also want to say that we have a fuller report, our final report on our societal readiness framework, publicly available on the C⁴U website. It's called Deliverable 5.5 to make it easy to find it, and it includes our societal readiness framework. And today I'll just highlight some key aspects of that broader framework. Ines, if you can go to the next slide. Thank you so much. Okay, so for any technology, for any product, readiness, whether there's implementation, depends on business, on society, and policy. But this is maybe even more important for CCUS than for many other technologies and products. CO2 is primarily, at least in this stage of maturity, still primarily a waste product. So it has, as of yet, little commercial value of itself. It's really the policies that will need to provide the incentives for industry to capture and ideally also utilize the CO2. So that's one point why society and policy have a large role to play here next to business. And the other aspect is that it's also potentially hazardous. So there are good reasons to look at all three aspects here. And it's really just if we can manage to combine all those aspects, policy, society, and business, that we can imagine successful implementation of CCUS. And so in our fuller report, we have, you can see the societal readiness framework as, let's say, a list of necessary conditions that need to be in place for CCUS to kick off. Yeah, the longer list is available in the report, but on the next slide, I'll just introduce some key aspects. So, for example, you can imagine if industry, what are the necessary conditions that need to be in place for industry to invest? Well, it's a business case and it's a level playing field. You can ask the same question for policy. What is necessary to impose effective policies that help provide the incentives that actually make it worthwhile to capture CO2 and store it or utilize it? Well, you need to have legitimacy for those policies. And you can ask the same question about society. What needs to be in place? What are the necessary conditions for society to support CCUS? That depends a lot on the trust that society has in industry. It's often, it will be taxpayer money that's also involved in investing in the technology. So there needs to be trust where that money is going and if it's well spent, and a fair distribution of benefits and burdens is another aspect that will determine societal support. We have investigated to which extent these necessary conditions are in place at North Sea Port. That's one of the case studies in this project. And in general, we think that there's a substantial level of readiness at North Sea Port, and that also comes from a long-standing good relationship between industry and the community there. But we also stress in our project the continuous point of attention, the continuous need for engagement between industry and society in many different ways on the local community level, but also on the broader level of the public debate. And on the next slide, I think if there's one thing that I would like you to remind from this presentation is that in our study, we also noticed again and again how strongly interrelated these different aspects are. And this is striking because in a lot of earlier studies, they are often treated as isolated. You either have a focus on industry or policy or on society, but they are so strongly interrelated that it's really necessary to have a more holistic view of how these different factors also influence each other. And if you look at this slide, you can see that it's so inherently interlinked because, well, industry will invest if there's a business case and a level playing field, but that really depends on those policies. There is a level playing field in a business case if the right policies are in place. The policies depend on legitimacy, and that legitimacy depends on the social support. It's the social support that will determine whether politicians can have the room to implement effective policies. And that societal support depends also on the authentic, genuine investments that industry makes and their role in the public debate and their behavior determines how the trust in the industry evolves and how the distribution, fair distribution of benefits and burdens is perceived. So that's all inherently interlinked, and that has far-reaching implications. The implication of this is that it's not just technologies and subsidies that will determine the implementation of CCS, but that it's really about how do these actors, what's the quality of the relationships between these actors. So if you think about how can you as an actor contribute to set this implementation of CCUS in motion, it's really a lot about making sure that there's enough trust between these actors, because that's really a high leverage point to improve the societal readiness that is needed to start investing even more in CCUS. And with that, over to you, Hannah, to focus more on the business case.
Thanks, Vincent. Yeah, exactly. We're focusing more on the business case now here and the supporting business model, which is obviously important to drive widespread CCUS adoption. So in this C⁴U project, we've looked at a very high level, the overview of the business model, and we think that there's three key components. So low carbon revenue generation, so whether that's leveling the playing field through policies such as the SDE++ mechanism in the Netherlands, or perhaps it's a steel plant that's selling clean steel manufactured using CCS with a green premium, so an additional cost for that decarbonized steel passed on to the individual consumer who's willing to pay that green premium price. The other important component is the ownership structure, so who owns each part of the value chain in the CCS infrastructure, so capture, transport and storage. Perhaps it's one industrial plant that owns the whole value chain, so they own capture, transport and storage. Perhaps they outsource it to a CCS as a service company, which deals with the capture, transport and storage part of the value chain, and the industrial plant just pays them a fixed fee, perhaps per ton of CO2 captured. Or perhaps there's an independent transport and storage company, so the industrial plant is responsible for the capture of the CO2 and then passes that over to an independent transport and storage company. And then finally, the third key component that we thought about was capital funding sources, whether that comes from government grants, whether it comes from private investors, from banks, from equity firms, or from venture capital type sources. So just in context of the C⁴U project, obviously technology research and development of carbon capture technologies is important in this business model, because it helps reduce or further define the costs of capture and provides that certainty and cost that's needed for both the industrial plant to invest in CCUS, given the ability to generate revenue from the low carbon product, but also certainty for investors investing their capital in CCUS. So then if we go on to the next slide, we thought more about how the business models may evolve as the European CCS market evolves. So we expect that for different industrial plants at different points in time looking to deploy CCS, the business model or the most viable business model will vary through time. So from a small scale CCUS market on the bottom left of this diagram, where we're looking at first of a kind CCUS projects, to a more mature CCUS market where CCUS is widely deployed in the necessary industrial plants. So if we look at the top line, we considered things like in terms of revenue generation, transitioning from more of a subsidy revenue incentives to more towards a taxation revenue incentives. And then in terms of the middle section in green, which is to do with ownership structure, transitioning more to carbon capture as a service providers or CCS as a service providers as the market becomes more mature and widespread. And then finally, in terms of capital financing, we considered things like private equity first movers transitioning to a more free market private equity, and public grants and loans transitioning out as that private equity and private debt becomes more important in funding the CCUS projects in a mature market. So then if we move on to the next slide, this is just the key takeaways from both Vincent and I's presentation. So obviously CCS is a necessary technology to reach net zero, but as Vincent mentioned, early and continuing engagement, particularly with the public, is key to successful deployment. In addition, we need this viable business model to ensure that products manufactured with CCS can be cost competitive, and there's incentive for an industrial plant to invest in CCUS. And we consider that over time, these business models are expected to transition from ones targeted at first of a kind project towards more self-sustaining business models in a widespread mature CCS market. I know Vincent mentioned his deliverable 5.5, but we've also written 2 policy briefs which summarize our work done in this project. One on the business models and things that I've talked about, and then Vincent's one on how to incentivize CCS in a society acceptable way. So thank you very much. And then I think the next slide, we're moving on to our panel discussion.
Indeed, many thanks, Hannah, for the fantastic presentation as always. And yeah, let's start now with the panel discussion. But before, let me start as well by properly introducing myself. My name is Inés Jiménez, and I'm a program officer at Climate Strategies. For those unaware of us, we are a knowledge workers organization working at the climate policy interface. We operate a network of over 100 climate policy researchers and are involved in a variety of research projects to tackle the climate challenge. So indeed, as Hannah and Vincent have so fantastically shown us, it's clear that CCS innovation and deployment depends not only on the technological readiness of these technologies, but on a broader ecosystem of factors, such as addressing society's perceptions of these technologies, as well as building a strong enough business case for them. I would like to continue this conversation by calling on our esteemed panelists for today, so that we can delve a bit more into this current dynamics in CCS deployment and how they are approached or navigated by different actors in the field. So I'd like to call F.R. Penot, Secretary General of the Zero Emissions Platform, Martijn Verloor, co-founder of Return Carbon and strategy advisor for Smart Delta Resources, and Jeroen Schuppers, senior expert in the clean energy transition for the European Commission's Directorate General on Research and Innovation. So let me just once again thank you very much for joining us today. It is great to have you with us. And so let me explain a bit what we're going to do right now. So what I would like to do is to call on each of you in order and invite you to provide a quick reaction to the research that has just been presented, and then answer a follow-up question to hear more about your perspective on the matters at hand. Then, of course, I'd like to remind everyone that we will have a Q&A session right after this panel. So you're more than welcome as audience members to bring up your questions. And you're also welcome to add them throughout the session already. So, Eckhard, I would like to start with you. You are Secretary General of the CEP, the Zero Emissions Platform, the official advisor to the European Union on Industrial Carbon Management, and coordinator of the European Technology and Innovation Platform. So, as the Director Secretary General of such a crucial convening force for the carbon management community, I'd like to ask you, what is the perspective of this community on the current readiness for CCS deployment in Europe, and what are the main priorities to push the way forward?
Great. Thank you very much, Inez, and good morning, everybody. Thank you so much for the invitation. It's a pleasure to be here and representing Zero Emissions Platform. I find the project is extremely interesting, particularly focused on the steel sector. So I'm going to kind of adjust a lot of my remarks, particularly towards steel, as it's really a sector that we haven't seen a lot of activity on when it comes to carbon capture and storage, unfortunately, in terms of project announcements and whatnot. But I think firstly, I'd like to say that in general, with regard to sort of the readiness, as you mentioned in the question, in your question, that we know that carbon capture and storage is a well-established set of technologies. There's over 50 million tons of CO2 that's being captured and stored every year globally. And I think it's firstly and really always important to recognize that a lot of these technologies and processes that are involved with them, so the capturing or the separating CO2 molecules, the transport, the storage, all of that isn't really new. Like a lot of the technologies are over 100 or up to 100 years old. You know, the first amine solvent or even amine patents, for example, were kind of put forward there in the 1930s. And I think what we're really focused on now, as Hannah's excellent presentation kind of tried to allude to, is finding some form of a business case to taking technologies that are not very new, but applying them in a way that sort of serves a benefit towards the climate. And I think what's really important is that, you know, we've had a lot of momentum in the past in Europe, certainly 10, 15 years ago, almost all of which was focused on the power sector. And I think what's really changed now is actually a real focus on the industrial sector as the place where we recognize that the need to do carbon capture and storage. And the reason for that is quite simple. You know, in the power sector, there are many different options available, both in terms of providing variable renewable generation as well as also firm power. And we've seen, you know, only recently some carbon capture and storage sectors and projects in the power sector, you know, in the UK, for example, taking FID. But what's really changed is in the industrial sector, and in particular in looking at sectors where there are emissions that are what so-called hard to abate, but really what we could say is also difficult to electrify. And we see that, you know, in the cement sector, where there's these sort of emissions that come from the limestone being produced that cannot be avoided through other means. And that's been sort of where, at least politically, there's been sort of a momentum in understanding that we need to deploy it there. But I think what we see now, you know, with the back of the EU Industrial Carbon Management Strategy last year, as well as the Net Zero Industry Act, is now we're getting to a greater understanding of the need, firstly, for carbon capture and storage, and also the key elements that go in that. I think one thing that's really key, obviously, is developing storage capacity. That's something that, you know, we was recognized now as a policy priority in and of itself, developing storage capacity within the NZIA. But now with the back of the Clean Industrial Deal, and I suppose a new commission, new ideas, and kind of recognizing Europe's place in the world more broadly, as well as the industrial sector. I think there's three key things here that, and some of which is really for policymakers to address, but a lot of it is also for the CCS community itself to focus on. So the first is obviously on the business case. So we see, you know, the real focus on, okay, products. So what happens is now we have the first of a kind projects. Let's say Heidelberg Materials have their project in Norway in producing or going to produce net zero cement later this year, and then they want to try and sell it on the market. And the problem is that when they're trying to go onto the market to sell this cement to buyers, basically there's no legal ring fencing for their product. It has to compete with every other product that's on the market, conventional, you know, high emissions intensity products. And so what they have to do is obviously trying to label it themselves, trying to market it in a voluntary sense, but really they're depending on the goodwill, so to speak, of construction companies in wanting to buy this thing. And that goes the same for fertilizer producers, and also for steel producers as well. And then when we get into sort of the trade element, which is really out of control, out of our control, you could say, in terms of how we can, you know, adjust these things. But it's very much what do you do when, you know, there's an overcapacity of steel on the global market, and what can we do to try and address that? The second element is probably something that policymakers could address, is more sort of the regulatory certainty. So Vincent and Hannah's presentations kind of alluded to the sort of cluster model. In the past, a lot of it was sort of single chain source and sink projects. So it was one company doing everything. We kind of recognize that probably from a de-risking perspective, it's probably better if different companies do different things in the chain, because then, you know, they have less to do, so to speak, and less investment risk to take. But what that creates a problem, though, is the coordination of that. And that's something that in the UK, they've really spent a lot of time working on, and it seems like they've kind of figured out in terms of how to focus on capture and then sort of transport and storage separately, and then the government kind of creates these contracts. Now in Europe, it might not be optimal to do it that way. There is probably going to be a regulatory framework for CO2 transport put forward next year, that will look at how we can kind of address the issue of sort of access and tariffs and things like this, in the same way that we focus on it in the gas and electricity and hydrogen markets. And then I suppose the third element is really something that the sector itself will hopefully get to grips with and better understanding in terms of knowledge sharing. And that's really understanding how these projects actually work at scale. So like I said, carbon capture and storage isn't new. A lot of the technologies are already being used and the processors are being implemented all over the world. But what is different is the uniqueness of the business models. So we have these really shiny new ships from Northern Lights, for example, that are ready to carry CO2, but we haven't actually had an at-scale business model showing like how this actually works. And I think the most important point to mention here, particularly when it comes to knowledge sharing, and understanding, okay, there's a technical element to it too in terms of like specifications, but what really is important is that we communicate to the public that in a lot of cases with these projects, companies are doing it for the first time. And so we need to really understand that like mistakes will happen. And the first time you do something is probably not going to be the best time you do something, but you're going to learn how to do it better in the future when it comes to building the projects, when it comes to operating them in the future. And that's really where the costs will hopefully come down and the efficiencies will increase. So I think those three things are kind of what gives me some optimism for the future. There is a little bit of pessimism in there, of course. I think certainly the trade element is something that will have to be addressed, but that's a much broader question. But hopefully that gives you some insights, at least, in kind of how we are thinking about this sector at the moment.
Thank you very much indeed. I think that is absolutely fantastic and a great way to outline the current challenges of what, as you said, is not a new technology, but one that is facing new challenges and new necessities as well. I'd like to jump straight into our next panelist for the session, which is Jeroen Schuppers. Jeroen, again, great to have you with us. You're a senior expert for the European Commission's DG RTD, which is providing support for research and innovation for the clean energy transition. Now, continuing on this conversation, the EU is facilitating much needed research and innovation for CCS, including through the Innovation Fund. But as we've been discussing now, the advancement towards scale up and the commercial deployment is not without challenges. So I'd like to ask, from the perspective and experience of DG RTD, what are the main barriers and opportunities for CCS technologies to scale up towards the commercial stage?
Thank you for this question. And first of all, apologies for not being able to switch on my camera. We seem in the Commission to have some issues with Zoom, at least I have at the moment, so that doesn't work. First of all, to start with, congratulations with the projects, and happy to meet again with Professor Haroon Margarethe. We have a longer history. We worked, or at least we were in contact with the old CO2 bypass project already in FP7, so it's a pleasure to see you again and see that you're going on. First, two small comments on the project as well. It is a very useful project to start with before I answer your question. I think two important issues that you address are indeed, first of all, CCS in industry. As Edward already mentioned, this is going to be more and more important, and this is as well reflected in our research support, and also the inclusion of those different industries in clusters to share an infrastructure. I think the project contributes significantly to that. It's important to share infrastructure also in terms of cost effectiveness, but it has issues with CO2 composition, flow rate, intermittency, symbiosis, etc. So that's very relevant. The other aspect of societal readiness is very important, of course, for any new technology, but in particular for CCS. And we try to mainstream that as well in our research programs. And I think for CCS, this is important that the projects and the researchers bring this message as well, because politicians normally are not seen to be the best messengers of bringers of the message that CCS is useful. You have to create slightly different view maybe with the audience of why we are doing this. It was already mentioned that we're not doing this for the power industry anymore, but to to work with industry, and therefore you have to underline the narrative that matters to citizens who are concerned with environmental issues related to industrial activities, and you have to develop a narrative that matters to politicians in political timescales. So you have to embrace a new political narrative that relates CCS to both industrial decarbonization, but also competitiveness, industrial growth, and employment. So projects like these can help bring that message. Now, on your question, what are some of the barriers and bottlenecks that we're looking to? I think a key bottleneck for CCS in Europe is, as was mentioned already, I think, is the lack of a well-developed CO2 transport and storage infrastructure. I mean, we have been working with research to reduce the cost of capture for many years, and there is still a lot to be done for the future. But I think the technologies are already there to do CCS. We see projects coming on. So any kind of research on those technical issues very often is for the longer term. What we need to do now is accelerated deployment. And therefore we have, of course, a Net Zero Industry Act, which was already mentioned, with the objectives of having 50 million tons of CO2 injection capacity by 2030, and the industrial carbon management strategy that helps translate that into research and innovation. And this is what we try to do as well. This is where we provide an opportunity, let's say, to help solve this issue through Horizon Europe, the next work program, I should say, 2025, which will come out very soon, will directly support the NZIA and the ICM, the Industrial Carbon Management Strategies, by focusing on a number of issues. First of all, we will continue to reduce the cost of capture, but we will also look at the effect of impurities in the CO2 stream, because this is going to be important in looking at bringing different CO2 streams together. What is the impact on the infrastructure in terms of not just corrosion and issues like that, like multi-phase flow, but also what is the effect in the reservoir, for example. And any kind of research that will help to set standards is very, very useful. Then knowledge sharing was mentioned by Edward. It's a very important thing. I fully subscribe to that. We have to take the lessons from the first movers that will help, first of all, to drive the cost down, as we have seen in Canada, for example, as well in Boundary Dam. The learnings there will allow for cost reductions in a next plant of about 30%, but it will also feed back into research programs because it will help to identify gaps. And coming to the storage potential that was mentioned, this is very important. And this will be supported by, first of all, we support it through supporting the geological surveys in Europe with a big project to help mapping of geological storage sites, but we will extend that with the support to an European EU-wide investment atlas for potential storage sites. So that will be looking at bankable storage sites. Now, what we can do further is work with member states very much on trying to roll out CCS. In the Industrial Carbon Management Strategy, it's mentioned that we will work with member states as well to see if we can have an important project of common European interest. And this is a very good way as well to release member state funding for these projects. And the zero emission platform stakeholders that are represented by Edward already mentioned that in one of their policy papers that they will be ready to support this. So this is a great thing to take forward. On the research side, coming back to that, we strongly will continue to put emphasis on industrial CCS, development of hubs and clusters as well. We will have it open in the 2024 work program. We also think of repeating that type of research in the future, because what we have seen is that Horizon Europe and the continuation of that into the Innovation Fund, which is much larger budget, have been very much instrumental in bringing projects in the CCS in the industry, in steel, but in particular in cement as well, to pre-commercial deployment. So this is important to continue, and I think this is promising that the ETS with the rising CO2 price at least is a very good source of deployment for that. Back to you. I leave it.
Many thanks, Jerome. And then very important points, and I'm very glad to see there's already some commonalities across this panel, such as the importance, as you said, of knowledge sharing and storage capacity. And yeah, just again, the main idea that these technologies need some advancements, but they're not new technologies, and there's many new challenges now related to competitiveness, industrial growth, and the employment, which are now putting at the forefront of this debate. To continue this conversation, I'd like to bring Martijn Verdot into the panel. Martijn, you're a former senior advisor to Smart Delta Resources and project lead across some projects such as Carbon Connect Delta and NordCap CCS, as well as the co-founder and director of Return Carbon, a project developer and investor in carbon removal and utilization projects. I'd like to ask you, as someone with such direct experience in financing CCS deployment, how would you describe the current commercial landscape for CCS, and where does the market currently stand?
Yeah, thanks, Ines. Happy to be here participating in this panel discussion. I've been engaged with the C⁴U team for the last several years, I think, both on the societal acceptance work that Vincent was talking about, and some of the analysis that was kind of cluster specific for North Sea Port. I've been working with the North Sea Port industrial parties for the last 4 years on their CCS project developments. Carbon Connect Delta was an example of that, where we tried to aggregate volumes from the cluster as a whole and transport it to potential storage locations. And throughout, say, the C⁴U project, we've had several engagements with stakeholders in our cluster, actually trying to work together with Vincent and the team on putting these stakeholder and societal acceptance models together. I'll say a few things about that, and then I'll come to the commercial landscape, because I think the first one also is quite relevant for the business perspective on this. And you know, traditional kind of stakeholder management, very simplistically, is quite static in a way. You identify stakeholders, think about what the message is and what the objective is of your stakeholder and how can you influence it. And what Vincent illustrated before is that this is a dynamic system with relationships and interdependencies. And just having some research done that establishes that as a systemic approach is very important. I think from a business perspective, the real next step is then, well, how do you use that, right? So how do you learn from being able to take action on some of these dependencies, and then understand how in a year's time, or 2 years' time, actually that system has changed in relationships, and do you need to kind of prioritize your actions somewhere else? Business in general is always about taking action and then learning how to adapt. And actually that is also what I see from the commercial perspective, and was alluded to before, but I'd like to touch on 2 things which are really quite critical from the business perspective. One is how to deal with risk in investment decisions. And the other has to do with this element of an aggregated system. I think both have to do with the fact that both are challenges, because we are looking at these kind of value chain projects at the moment. They're integrated across the value chain. You have to take a decision from emitter all the way to store, and that introduces kind of risk across the value chain, not only in terms of price, and some of these contract for difference, the SDE++ in the Netherlands is an example. Some of these contract for difference frameworks will help mitigate some of that risk on price. But from a business perspective, you're always also asking the question of what if something happens with the system as a whole? What happens if it's underperforming, or even what happens if it breaks down? And if it breaks down in a part of the value chain that's under your control, then actually the business itself can take a risk-based approach on that investment. But if it happens, if the breakdown happens in another part of the value chain, then you need to have some sort of recoup mechanism for the capital that you employed. And this is where if everybody across the value chain has this challenge, then there's a real difficulty or a dilemma in trying to get to a decision on an integrated value chain. And this is what we've seen, and I've seen in some of the discussions that I've had around heads of terms and contracts between parties. These contracts for different schemes help, but there's something around trying to provide an insurance against these quite unlikely scenarios. But from a business perspective, you need to be able to mitigate against the potentially very large value impact. So that's one. The third thing I think I'll share is around this aggregation. This is a real a challenge where storage operators have to create relationship with multiple emitters in order to get to threshold volumes such they can take an investment decision to actually build the offshore facilities. And the offshore facilities could be platforms, wells, could actually the same holds true for pipelines. And on the aggregation of those types of partners in such a system, it's very unlikely that everybody will be able to achieve a financial investment decision at the same time in order to get that threshold established. And that convergence of timing is a real challenge if that infrastructural piece in the middle doesn't exist. And this is what happens in these integrated projects. A lot of time is spent across the value chain to understand how some of these timing risks can be mitigated and still proceed. So I'll leave you with those kinds of reflections, a very business-focused perspective maybe, but of course it all is contingent on what Jeroen and Edward talked about before, that you have a framework, a regulatory framework within which you can operate as a business. Over to you, Ines.
Yeah, fantastic. Business focused, but a great contribution nonetheless, and raising very important points, not only, yes, against the importance of a regulatory framework, but also the challenges that come from an integrated system and the kind of risk factors that go across the supply chain. Well, many thanks again to all the panelists. I'd like to now open the Q&A session. So I would like to ask all attendees if they're interested in raising a question to either share it in the chat, or I believe you should be able to raise your hand and bring the question up to us. Please note that you're allowed to ask questions to our presenters, including Jeroen, who is unfortunately not able to turn the camera on, but still available for this moment. All right, I see that Harun would like to pose a question first.
Thank you very much for the panel. I think it's an absolutely excellent presentation of the state of affairs across the board. And it's great to see friends also. Jeroen, very nice to see you, and thank you for attending this presentation. I think one thing that I would like to ask the panel is the delay. When we are talking, Jeroen, for example, he mentioned the fact that we are looking, the transport is an issue, of course, that one needs to consider transportation and storage. And the impact of time, because there is always a lead time. When you're laying pipelines, for example, you're looking at about 10 years from this conception until production and operation of the pipeline. Storage sites, for example, also, by the time you explore and determine the viability of the storage site until it becomes operational, we're also looking at a significant lead time, 10 years maybe, some estimates are. So how does that impact as far as the meeting of net zero emission targets is concerned? This challenges. For example, when it comes to ship transportation, we are not looking at that much of a lead time as compared to pipeline. So has that been factored in? Maybe I'm...
Yeah.
Yeah.
I can have a quick reaction. This is indeed, Harun, a very important question, lead time for not just infrastructures, pipelines, but also for storage sites. It takes a long time. Now, there is very little, of course, that research can do to speed that up. Let's because it's very often not research. The only thing that we can do to help speed up the storage lead time is to look at have a better inventory of storage readiness and storage, let's say bankable storage, which we're trying to do. But on the other end, it is very much linked to permitting issues that can be very long. We've seen that in many other clean energy technologies, that lead times for permitting for wind energy, for solar as well, are prohibitively long sometimes, and that can sometimes make projects difficult. So this is why in the Net Zero Industry Act, it's member states are called upon to accelerate their permitting procedures. If the member states assign certain projects as net zero strategic projects, for example, then there is a maximum of so many months, 12 or 18 months, for the permitting for those projects. So that will help to speed it up enormously. I think that is just on a regulatory issue, but I'm not a regulator, of course, but these are things that that can be changed. Although I have to say, certainly for issues like CCS, which can be sensitive, you cannot just speed up permitting, let's say, without having to look at the public concerns for safety, etc. You should always do that within the right framework. But this is my answer.
Thank you very much. I don't know if
maybe Arun, I can
much...
add a perspective there. I think from a business side, it's it's important to have options, right? Alternatives. And that is so. Of course, that's difficult in an early market. But if you have alternatives, then you can assess the opportunity and risk of one option versus another. So, waiting for a pipeline infrastructure to be built versus going faster with a maybe slightly more expensive option through shipping across distances. But if it's 3 or 4 years faster than the alternative, then that actually may be a good and wise business decision. So having alternatives available in a market where emitters are, trying to get to investment decisions is a key enabler sometimes.
Great addition indeed. I'd like to now open to other audience questions. I see that Pratik Saha has raised a hand, so you should be able now to bring your question up.
Yeah, I'm just wondering, can you hear me?
Yeah, all good.
Okay, yeah, thanks. Yeah, I have essentially a couple of questions. The first is, we kind of alluded to that earlier in the conversation. First question is this green label that we're going to be putting on the product. So let's say green cement or green steel. Do we have an appreciation of how much the international market is willing to pay for this green premium? So my question really is, how much appetite is there internationally to pay a premium for this green product? And I guess secondly, on the back of that, do we then have an idea of, how much sort of private equity or private funding would come into the development of these projects? Because I guess the two are linked, right? Yeah, that's essentially my first question. Yeah.
I can start with the answer to that. I guess I wouldn't necessarily say the two things are linked. I think there's two parts to the question. I think the second part that you asked, how much private equity or private debt financing is available, I think that all depends on, a bit like Martin was saying, investors make decisions on what to invest in based on the risk reward ratios. So if there's higher risk and there's higher reward, maybe they would invest. I think CCS at the moment is still quite there's no certainty in the revenue generation, so it seemed in some cases, there's less certainty in revenue generation, so it's seen as more of a risky investment. In other places where you do have more certainty in revenue generation, for example, in places where you have the SDE++ contract for different support mechanism, if you can show that return on investment, you can leverage a wider pool of private investors. I think back to your first point on the green premiums, I wouldn't want to put a price on exactly how much people are willing to pay for green steel or green cement. I think one thing that we're really seeing here at ERM is that companies looking to decarbonize their scope 3 emissions. So like Microsoft building data centers, like the Nobel Museum, which is looking to procure green cement from Brevik CCS. I think there's actors like that. So maybe conscious consumers, but also local governments that have set scope 3 emission reduction targets are really looking to procure these decarbonized steel and cement, etc. Exactly what price they would be willing to pay for that, I think depends on how willing they are to, or how ambitious their scope 3 reduction targets are. So I wouldn't want to put a price on it, but I think that's definitely a big market driver that's coming in that we've seen in the last couple of years for the green premium side of things.
Fantastic. Oh, I see Epard wants to go on.
Yeah, I would just say as well, like it really depends, and I know this is an annoying answer, but it really depends on the market. So in the cement market, it's different because firstly, they're less globally sensitive because you don't see concrete being shipped around the world because it's so big and heavy, right? Aluminium, steel, fertilizers to some extent are different than that because they're higher value products and they're lighter and easier to transport. But what's really different is the buyers in the market. So if you're a fertilizer producer, your buyers are not the big, massive food companies like Nestle. They're farmers, and farmers, like everyone knows, have been really, in challenging situations with their margins being cut for decades, and they're selling their food downstream to the food companies. So the appetite, let's say, or even the not just willingness to pay, but ability to pay a premium for, say, low carbon fertilizer, which isn't technically difficult at all. I mean, it's basically just adding transport and storage to a pure stream of CO2 that's being vented, in most cases. It's not difficult to do these projects. What's really difficult is actually figuring out how to deal with that. And I think in the cement market or in the concrete market, it's also, you do see willingness to pay among big corporate buyers, like in the tech industry, for their data centers, for the construction projects. But they want a label, they want a certificate to see that this thing is different than just buying regular concrete and cement. Steel is another one. They have actually, the steel industry has done well in developing a label now, firstly in Germany, and now it's going to be adapted into the European level, which basically even has several degrees, and sort of it comes with, a product labeling. But most of the buyers for steel in Europe are the car industry. And the car industry in Europe is struggling quite a bit because of, they missed the boat, let's say, in electric vehicles to some extent. So there's all these different things happening all at once, basically. And I think what's important to recognize is, firstly, I mean, the main thing to recognize is the users of, or the initiators, let's say, of carbon capture and storage projects in Europe are primarily emitters, because they look at the ETS, the emissions trading system. And so the reason why they would do a project is not to make money, is to shield themselves from paying the carbon price. So it's like doing energy efficiency in your house and not having to pay higher energy bills. You're not making extra money, you're just saving yourself having to pay the carbon price in the future, maybe. In America, it's very different. In America, you're paid to put CO2 in the ground. So your revenue model there is clear. You're looking to profit from it to some extent. So the idea of trying to sell these products at a premium, because they are different, because they're low emissions versus conventional ones, is actually adding in a different revenue stream to make your project more bankable. So I think the more that policymakers can do, and to be honest, most of this will come from national governments, because in many cases, such as in construction, it's the government that's building a bridge and a big concert hall or football stadiums or houses or whatnot. They operate, or occupy, let's say 20, 30% of the market in some cases. It starts with the government actually being willing to pay for these types of materials, particularly in construction and possibly in other sectors as well, where they are the buyer. And it's about reforming sort of the procurement rules that go with that. And that's probably where you will see hopefully some changes in the coming years, because the ability to pay is much higher, certainly from those, some big corporate buyers, like I said, but also from the government itself. So hopefully that adds a bit of clarity or color to Hannah's really good answer as well.
Many thanks, Hedbert. I think indeed there was this perfect clarification to add as well. We're technically over time, but I'd like to maybe ask for a very concise answer to a question that's been posted in the chat at the beginning of the session, which is from Yasha. What are your observations from Northern Lights project in terms of formulating a business model for C⁴U? So if there's any quick takers, maybe? No brave souls from this panel wanting to take this question?
I think that,
well, yeah, I can
oh, you go, Martin.
share a perspective maybe, but the Northern Lights, from a pure business case perspective, is enormously helped, right? Because if you take the industry perspective, of course, there's a disproportionate amount relative to some of the other policy frameworks in place and subsidy frameworks in place that went into the project from the Norwegian government. And so you could almost regard kind of the case that underlies the decisions for Northern Lights as a bit of a one-off, but a critical one, because it demonstrates to the market that it's possible, it works, parties are willing to commit, and some of the contractual structures that have been negotiated will set the tone for future discussion. So from a, say, pure financial perspective, it may not be the most representative business case, but from a framework perspective, it's definitely quite very important.
Great to hear. Fantastic. Well, I'd like to once again thank our esteemed panelists, speakers, and everyone that's posed the question for this session. Unfortunately, we've run out of time now. So I'd like to move on to the next part of this event. As we have discussed, there are many factors to be considered for the successful deployment of CCS, but at the core, we still have a technological question, which is how to surpass the techno-economic challenges and build a strong case for deployment. So I'd like to now give the word back to Harun, as he will introduce our next session dealing with this question. Harun, over to you.
Yes, thank you very much, Ines. And again, thank you very much for the panel for their discussion and contribution to the meeting today. So as Ines said, now we dwell on the technological challenges. Techno-economics, of course, you need to develop the processes and the technologies that are needed to ensure cost-effective, benign technologies that can challenge the capture of CO2 from the steel industry in the context of industrial clusters. So we are talking about not just capture, but also transportation and also storage. So the rest of today, we will focus on the work that has been done in the context of these technologies. As I mentioned briefly at the beginning of this presentation, when it comes to the capture of CO2, we are dealing with a unique set of challenges because of the nature of the CO2 and the flow rates and the high temperatures. Impurities were mentioned as a major challenge. It is not possible or extremely difficult to develop one single capture technology which can handle all these different CO2s with different compositions. So what we've achieved, and I think one of the main successes or stories of C⁴U is the developing two technologies which are capable of handling almost 90% of these CO2 emissions coming from the various points in the steel plant. They are basically solid-based technologies which overcome some of the issues with solvent aggregation. So we will dwell in the first capture technology that has been developed in parallel with another one, the two capture technologies. The first one is displaced capture technology, and our project lead on that aspect is Gianpaolo will talk about our work on the displaced capture technology. This will be followed by our next speaker, Professor Carlos Avenidas from Spanish National Research Council, who will talk about the parallel technology, the handling CO2 emissions from the blast furnace and other emission sources in the steel plant. This will be followed by a break, which we will follow on with a presentation from TNO on the sorption-enhanced water gas shift reactor. Basically, it's a technology which produces blue hydrogen by combining the capture technologies with the sorption-enhanced reaction to produce hydrogen more cheaply than green hydrogen and economically. We talked about the issues regarding the transportation of in the context of industrial clusters. So we will continue later with the design and operation of CO2 transport for CCS, followed by question and answers and closing remarks. So without further ado, I pass the floor to our Professor Gianpaolo Mazzolini from Polytechnic Institute in Milan, who will talk about our work on the displaced capture technology. Over to you, Gianpaolo.
Thank you very much, Arun. Thank you for your kind introduction. And thank you all for attending this event. It's a privilege for me to be here to present the results of the displaced capture technology, which was developed in the C⁴U project. And I'm presenting on behalf of all the partners who contributed to the development of this concept throughout this 5 years project. So before talking about the displaced capture technology, I want to discuss briefly why we need a new capture technology. And I will do it through this slide, which presents the general layout of the blast furnace, basic oxygen furnace concept for producing steel. This is the most diffused technology worldwide, and it strongly relies on coal and coke as primary energy source. There are several processes where reaction takes place, and together with the processes, there is the distributed generation of CO2 emissions in several places. In addition, as you can see from the table below, these CO2 sources have different conditions in terms of temperature, in terms of mass flow rate, as well as the most relevant one being the composition. The CO2 concentration can range from 10–15% up to above 42%. The rest of the gases mainly consist of nitrogen and steam as consequence of the combustion. So the technology we develop, and it has to be developed, requires to be flexible and operates under these extreme distributed CO2 emissions and different operating conditions. But in a nutshell, here are the features that has to be tackled by the technology developed. We have many emission points in atmospheric pressure, so the technology in this case should be a post-combustion technology. Then the CO2 concentration ranges between 10 and 40%. So we need the technology which is flexible against this variation of concentration. The CO2 has to be produced at high purity for transport and storage reasons that will be presented later on. So we need a capture element which will have high affinity with the CO2. And last but not least, because of the strong emissions, it's a very CO2 emitting process, around 2 tons of CO2 per ton of electric coil. We need technology which has lower energy penalty and cost than current technologies. So this is the framework. This is why we needed to develop a new technology, and this technology is called displace. First of all, it is a solvent-based technology. As you can see from the bottom left here, this is a picture of the sorbent adopted, and this is the element where the CO2 is captured. So how does it work? We have the exhaust gases, where I showed before the presentation, the composition mainly consisting of CO2, nitrogen, and steam. These gases are collected, goes through the reactor where the sorbent is placed, and the CO2 stays absorbed on the sorbent. And this is the first initial step, which is the absorption step. So it the absorption is at constant pressure and constant temperature, so the CO2 remains connected to the sorbent while the other inerts are released. When the sorbent is completely saturated, we need to detach the CO2 out of the sorbent, and this occurs in a new step called the sorption process, and the sorption step, and we need a new agent, a new fluid, in this particular steam, that takes over the position of CO2 on the sorbent. So we have in the end a high purity stream here, while the steam remains connected to the sorbent. This is the resorption step, and with respect to the other sorption-based processes, this is at constant pressure and temperature. So it doesn't need any variation of temperature and pressure. But what are those pressure and temperature that the displaced process should be operated? Looking at this graph, you see the amount of steam needed to capture and separate the CO2 at different temperatures. So here is a 300 degrees C, here is 350, and here is 400 degrees C. The lower the steam, the lower the energy needed to separate the CO2. So the temperature at which the system operates at its optimum is around 400 degrees C. And for the pressure, we can see that again, the minimum steam demand occurs for intermediate pressure range, so between 5 and 7 bar. Once identified the operating condition of the displays, the next step is to see whether it can capture CO2 at a very high purity. And this graph shows you that it can be achieved, surely depending on how much steam we used to clean the bed, but purity up to 99% can be achieved together with a very high carbon capture ratio up to 93%. So from lab point of view, modeling point of view, a new technology was developed capable of capturing CO2 at high purities and high carbon capture ratio. But the main goal of the C⁴U was to demonstrate the technology at TRL7. Here on the right, you can see hidden by all these elements inside the steel red structure, there is the displaced column that was tested at Sphering in Sweden, that is connected to a real steel plant by SSAB. The gases are taken from the steel plant, compressed for the operation, and then sent to the displaced process. Here is all the barrels containing the sorbent that filled the displaced reactor. In this graph, we see how the system operated during the testing. This was just 1500 seconds of experiments, but it lasted a lot longer, and we can distinguish between the desorption and absorption steps, confirming the stability of the sorbent. But what was more relevant is that if we compare the measurements here on the x-axis with the experimental results here on the y-axis, we can see that the points lies on this line. If they lie on this line, it means that what we were expecting was actually occurring in the demonstrator at TRL7. So this means that the experiments confirmed the technology at TRL7, which was one of the main achievements of the project. But after demonstrating it, we needed also to show whether this technology was more effective from energy, CO2 emission, and cost point of view respect to the competitive technology. And here are some results. These results are carried out assuming a carbon capture ratio of the system at 90% and carbon purity at 95%. As stated, this is a flexible system, so we designed this parameter just to perform some calculations. So the displace technology can achieve 80% CO2 avoided using reheating oven gases, while the MEA reduces the CO2 emissions only by 77%. So there is an advantage of the displace process, mainly because the additional fuel consumption for regenerating the sorbent is lower than the one needed by MEA. The same result can be achieved considering hot stoves as gases, while if we go for the sinter plant gases, which has more diluted CO2, the MEA outperforms the displace process. So CO2 avoided displace mostly overcome the performance of MEA. Going to the specific energy consumption for CO2 avoided, which is the additional energy for capturing the CO2, the displace with reheating ovens achieves a value of 2.9, which is more than 30% lower than MEA, again, because we have lower regeneration energy than MEA. So it has better performance, and the same, of course, when we assume hot stoves are gases, while for the sinter plant, the situation changes. But going to the most relevant parameter, looking at the costs, here is the cost of CO2 avoided for the displays, and we can see that they are 15% lower than the one of MEA. There is an advantage of CapEx, so the displays process is cheaper than the MEA. There is an advantage in fuel cost, additional fuel for generating the sorbent, which are cheaper than MEA. This is partially balanced by a higher electricity cost because of the compression work required by the gases. The same result is achieved for hot stove gases and displays, while for the sinter plant, because of the higher dilution, which penalizes the compression work, the MEA outperform the displays. So these results were achieved for a carbon capture ratio of 90%, carbon purity 95%. However, looking at the hot stove case, we generated the performance, changing the carbon capture rate from 90 to 98% and the carbon purity from 95 to 99%. The technology responded very well, certainly from cost perspective, increasing purity and carbon capture ratio, also the cost of CO2 avoided increases by roughly 10%. Going to the main take-home messages, within the C⁴U, the displays technology was developed and demonstrated up to TRL7, and it proved to be flexible against flue gas composition. Very high purity and CO2 capture were achieved, and in most of the cases, displays is cheaper than competitive technologies. So I want to thank you for listening, and I want to acknowledge the partners who contribute to the development of this technology, here reported, TNO, Kisuma, Sferins, and Food. Thank you, it's all from my side. I leave the floor to the other presenters.
Thank you. Thank you very much, Gianpaolo, for the presentation. There will be time for questions and answers later on. These can be posted on the chat line or also in person. So we move on to our next speaker, Professor Carlos Abanides, who will be talking about all the great work he's been done on the cathode technology. So over to you, Carlos. Thank you.
Thank you, Harun. Thank you. And good morning to everyone. Okay, my duty in the next 10-12 minutes is to summarize what we have done developing this cathode technology over the last 5 years. I have been the leader of Work Package 2 in charge of demonstrating this technology at TRL7. Next slide, please, Ines. Okay, this is perhaps the simplest representation of the process we intended to demonstrate in this project, the cathode process. As you can see, looking at the top of the figure, there is a first step, perhaps the most productive step, where we are going to treat blast furnace gases that, as mentioned earlier, are fully loaded in carbon. About 50% in their volume is either carbon monoxide or carbon dioxide. This is going to go through a bed of calcium oxide, where the reaction of carbonation should take place if the conditions are arranged for that reaction to go forward. Yeah. The carbonation reaction is capturing the CO2 from the gas phase, not only the CO2 that is already there in the gas, but also the CO2 generated in the water gas shift reaction taking place in the same bed. So the final product, as you can see on the right-hand side, is a hydrogen-nitrogen gas, a clean fuel gas, and this is the critical point for this technology. This is a multi-product technology. We are not only capturing CO2, we are generating something that should be of good use somewhere else. Now, what I have told you so far is, as it has been mentioned earlier in other presentations, all science, let's say, like the basis for this, believe me, for those of you not expert in this field, go back over 100 years. The innovation here is to come back to the original bed, allowing you to do these reactions, basically to regenerate the calcium oxide in the bed and the copper. And we do this by a second chemical loop. This is a chemical looping combustion step, where by oxidizing the copper and then reducing it with a fuel gas, we generate the necessary energy for regeneration of the calcium carbonate. If you click next again, Ines, yes, there are many versions of, or several versions of this process, and allow me to be cynical, like everybody working in emerging CO2 capture technologies, we claim, and so far you need to believe me, on paper, we claim that energy penalties will be lower and cost will be lower overall if you follow this route. Of course, the key challenge, next slide please, is to move forward to demonstrate these claims with any capture technology. In the next slide, Ines, in the next slide, yeah, I summarize basically on the left-hand side that there is a lot of background information at low TRL. We have generated a lot of new data in this project as well. And of course, you tidy up this information. Next, please, to create a design of the TRL7 pilot, the process flow diagram, even the 3D view. And unfortunately, next animation, unfortunately, this is typical in TRL7 projects. As our colleagues, Harun and other colleagues in the project will know, we have been late in the commissioning of this pilot, up to 18 months at some point in the project, because we faced many materialized risks. We avoided COVID, for instance, but we didn't avoid the cost escalation and the supply chain problems post-COVID. We have many technical issues. But in the next slide, and I think in the chat, there is a link already for the view of the pilot. We succeeded in November 2023 in passing the factory acceptance test of this brand new pilot located in the gas lab that ArcelorMittal has in one of its factories, this one in the north of Spain in Asturias. So I have no time to describe the pilot, but perhaps I move to the next slide, where another big important milestone for us took place in May last year. Now, from that messy number of curves from the pilot, you need to believe me that there were a lot of good results behind this data. For the first time, we achieved stable, looks paradoxical when you look at these curves, a stable operation in the key aspects of the pilot. And to prove this, in the next slide, please, you can just look at the happy faces of the people, the photograph that I took of those running the experiment from our institute and from the ArcelorMittal side. In the next slide, I have a single example of results from this pilot of the important CASO stage or CASO reaction state. Remember, we are, as you can see on the left-hand side, carbonating basically calcium oxide until we run out of calcium oxide in the bed in these reactions. And as you can see on the figure on the right, as long as we have calcium oxide, yes, the carbon in the blast furnace gases is disappearing from the gas phase. We are obtaining a nice stream, in that case, of 32% or so of hydrogen at the exit of the reactor. Of course, after 40 minutes or so in this example, calcium oxide has been finished in the packed bed, and you go back to the concentrations of the carbon in the blast furnace gases, while corrected by the water gas equilibrium. Now, we have accumulated 2,000 hours of operation experience, maybe not as good as this one, unfortunately, but no, let me correct myself. Bad experiments are also very good. This is research at the end of the day. Bad experiments means a lot of learning, and they are usually very good also for tuning reactor models. The curves, the solid lines that you see in that figure, are actually predictions from the reactor model we have developed for lower TRL. And as you can see, there is a very good understanding now from our side, demonstrated at TRL7, of the phenomena going on in in these beds. So 93% capture efficiencies are reachable. They can go even higher. We were allowed to go to higher pressure. Next slide, please. And most important, with this information, you add credibility. Now is a key word, credibility to the technical viability of the full capture system. This activity has been led by colleagues from Manchester University. Let me say here that we are not intended to reinvent the wheel. So when it comes to organizing these processes using packed beds, there is a lot of engineering knowledge behind helping us to create these designs. Basically, you end up always for a continuous operation, in this example, for a 1.5 million tons per year of production of CO2, you end up with a good number of parallel reactors operating in a synchronized manner with many valves opening and closing at the right time to allow this operation to go continuous. And of course, here we face the challenge that these valves require to be, and our original designs went to high temperature valves. And this has been a kind of turmoil in the project by the end because the cost of these elements, but we believe we have found, let's say, reasonable solutions, and a further improvement is awaiting in the future. So my last two slides, I think, are then moving to the cost. This has been led by colleagues at Politecnico di Milano, Gianpaolo's group. Nicola Zecca has completed his PhD with these studies. And it's very important that you look at the numbers in this public deliverable in detail, right? Because if you don't look in detail, you may be tempted to run away from my presentation when you see what I'm going to show you on the right-hand side of the figure. Basically, we are using the reference case. Yeah, it's a solvent case similar to the one that Gianpaolo has presented, which is around 106 euros per ton of CO2. And your first impression is awful, isn't it? Like CASO technology seems to be something going over 250 euros per ton of CO2. Now, this is the time for you to look to the same figure on the left, where I'm doing graphically the subtraction of what is cost, the same positive bars than in the figure on the right, and what is revenues, what is value coming from the additional products coming from the CASO technology. The hydrogen, nitrogen field gas, of course, has value. The steam coming out from high temperature flows and other savings, other elements. Now, still, this comes with this disappointment. Let me be clear, because we are still, we seem to be still more expensive than the reference. Yeah, about 30% more expensive. Let me stress that this cost analysis comes with a lot of really relevant and reliable data from our industrial partners in the project, mainly Wood, that fed a lot of information to this analysis. So in the next slide, I want to emphasize the key points here when assessing cost of CASO. First, don't do CASO, don't do anything with this technology if you cannot give value to the side streams other than the CO2. Yeah, if you don't know what to do with this hydrogen-nitrogen mix or with the steam, don't do this technology because, yes, it's going to be very expensive. And the other way around, if you are thinking about linking these systems with ammonia production or with other processes where you can make a good use of hydrogen-nitrogen, have a second thought and look at the next slide, please. First, we know that the CapEx, our CapEx deviation is linked to these high temperature valves issues and even some over-the-top compression steps that need to be readdressed, let's say, in future studies. But the main element, and next slide, please, the main cost element in the CASO technology, and this is something that I debated extensively with colleagues at Polimi, and they are right, this is just fair play, is that because you are no longer using blast furnace gases and other off-gases for power generation in the steel mill, the CASO technology is obliged to kind of import all the electricity in the steel mill and pay for it. Yeah, that's why, and pay for it and take care of the carbon footprint associated with that electricity. So this is why this number is so big. 100 euros per ton of CO2 comes just from that kind of fair play analysis of the cost of cash flow in this scenario. In the next slide, please, if the electricity, the same electricity without keeping exactly the same design of the process was renewable, if you go to a scenario where that electricity import is renewable electricity, then we are already break even. And in the next slide, if that electricity is low cost, and believe me, in some places in Europe, like in Sweden, and maybe in some places in the south of Spain or in the south of Europe, if that renewable electricity is low cost and low carbon footprint, cash flow becomes an extremely attractive technology. So my last slide is just a couple of messages. Well, the first is that, yes, we know a lot more than we did, and we are quite happy with this technology now that the key steps have been demonstrated at TRL7. And when it comes to industrial scale applications, you really need to dedicate, I cannot give you enough information in this brief presentation, you need to dedicate time to assess the technology cost on a case-by-case basis, because this technology cost is extremely sensitive to your assumptions on electricity cost and your assumptions or the value that you give to the byproducts, yeah, including the CO2 high purity stream that we are kind of promising from the technological perspective, and the flows, of course, of decarbonized fuels and steam coming out necessarily from the application of the technology. And of course, the last bit of the second half of the slide is to acknowledge the huge work that has been done here by Work Package 2 and Work Package 3 partners in the C⁴U project to kind of move forward this technology to the point that is today. Thank you.
Thank you very much, Carlos. If you could just go back to the agenda, please. Ines, if you could just display the agenda. So we, just to add that we've had, in context of commercialization, quite a bit of success as far as the displaced technology is concerned. It is available for, the technology is available for licensing to the next stage. And there is also considerable interest from ArcelorMittal in the cathode technology to take it to the next step. So that is, I think, it's a very important achievement to make sure that the technologies that we develop see the light of the day and make a contribution to meeting the net zero emission targets. We are basically running late. My apologies for that, but I think it's now time for a short 10 minutes break. Can I please ask everyone to reconvene back in 10 minutes? That makes it, let's say, we are 11:40, 10 to 12. That's 10 to, just look at, I'm looking at the different times in UK, and so that's 10 to 12 UK time or 10 to 1 CET. So I look forward to seeing everyone back. Thank you very much. Good afternoon, everyone. Good morning also if you are in the UK. Our next presentation is on the sorption water exchange gas shift technology. Is Eric presenting, or we have a replacement today from TNO? I think.
Yes, I will be presenting.
Eric, you're Eric van Dijk. Thank you very much from TNO, who will talk about the gas water shift gas sorption reaction technology. Over to you, sir.
Okay, thank you very much, Arun, for your kind introduction. So thank you very much for this opportunity to talk about our C⁴U technology. And if you could do the next slide, please, Ines. Okay, yeah, you can do the next slide straight away to keep the pace somewhat. So I will be talking to you about our subsurface water gas shift technology, which is a CO2 capture technology that can be implemented, that we see as a platform technology, meaning that we can apply this technology for different kinds of industries, different kinds of feed streams, and also towards different kinds of products. So we can, this is a capture technology for pre-combustion systems, where we remove the CO2 from the stream and react the CO to completion towards a hydrogen-rich stream. Why I want to present this is because the displace technology, which has been developed and demonstrated in the C⁴U project, is actually a very specific application of this CWEX platform technology. Displace is really tuned towards post-combustion systems, so capturing CO2 from a CO2-rich flue gas, as has been nicely explained by Gianpaolo before the break. And now I want to dive a little bit deeper into the technology, similar type of technology, actually treating CO2, capturing CO2 from pre-combustion streams. So next slide, please. So the technology is based on a solid material that interacts with CO2, so that absorbs the CO2 and actually is active in the water gas shift reaction. And if you click on then, because this is an animation, so we have a solid material that takes up the CO2 and actually completes the water gas shift reaction, so producing a hydrogen-rich stream and a material that is loaded with CO2. If you click again, please, after this material has been more or less saturated with CO2, we need to regenerate that, and we do that in several steps. First of it is a rinse step, where we can apply a small amount of steam in order to improve the CO2 purity of the final product, of the CO2 product. Please click again. Indeed, this is a pressure swing type of system. So the adsorption is at high pressure, the regeneration of the material is at lower pressure. So we need some pressure equalization steps. And then the last step in this animation is the regeneration of the material by using steam. And because this is a process that is operated at elevated temperatures of around 400 degrees, we can indeed use steam as a medium to affect the water gas shift reaction, of course, but also the separation of CO2, and thus realizing indeed a high capture rate together with a high CO2 purity. So that's the fundamentals of this technology. Displace is a variant hereof, as has been explained previously. So next slide. So we have been developing this technology at TNO for quite some time already, and we are climbing the technology readiness ladder, let's say. We have had quite a few projects in the past, really focusing on understanding and developing materials, developing process models. And we are now really into the TRL 6-7 demonstrations in stepwise. First, the C⁴U project, of course, and the current project that is running is Initiate, where we will demonstrate a multi-column system using this technology. So next slide, please. So some words on Initiate. The Initiate project is started a little bit later than C⁴U, but it's still running, and it's also Horizon 2020 subsidized. It focuses on the demonstration at TRL 7 of the industrial symbiosis between the iron and steel sector and the ammonia and urea sector. And we do that by using the iron and steel residual gases as a feedstock for the production of ammonia and urea. So demonstrating this symbiosis system. Yeah, one slide back, please. Our vision is to create a bankable case for a first-of-a-kind demonstrator at the 50 kilotons per year urea scale based on basic oxygen furnace gas. And in the project, we will take all the steps that are required indeed for the development of this first-of-a-kind plant. So that means the demonstration of the technology, but also the site identification, business plan development, and collaboration agreements. That's all part of the project. So next slide, indeed. And click again, or a couple of times, because there's an animation in there, indeed. So these are the project partners, 11 project partners from 5 different countries. And we span the whole value chain from material suppliers to technology suppliers to end users, and of course the knowledge support in the form of universities and NGOs. We have a 5.5-year project, so April 26 is our final date. Okay, next slide. We are still constructing our pilot. The first campaign is planned for this year, but this is actually, as you might have recognized from slides of displays, this is the same unit in Sweden that we have adapted towards multi-columns. So the solvent materials, all the functional materials have been developed in the project and are delivered and are at site. And currently we are installing the reactors, and we are nearly ready for campaigning. Here you see also the ammonia reactor. We will demonstrate on site the whole value chain from both gas intake from the SSAB steel plant next door to this site, all the way up to ammonia synthesis. Okay, next slide. So a very important aspect of the project is indeed a long-term implementation plan, and this is a very interesting scheme where the most important cost drivers and the most important benefits are summarized. And there's some very important learnings from this graph. First of all, is that the benefits outweigh the costs. So there is actually a business case for this symbiotic relationship. What you also see in this graph is that there are also major costs, which are especially related to the CO2 storage and not so much for the technology, but really the transport and the storage is the main cost driver. And there are significant benefits because of prevented fossil fuel use and also premiums for prevented emissions. What's also important in this graph is the arrows, which indicate the uncertainties of these cost and benefit estimates. And it shows indeed that the direction of the arrow indicates also where the uncertainties are. So especially in the benefits, the uncertainties are towards larger benefits, and they mainly relate indeed to policy elements such as CO2 pricing and CBAM mechanism. Okay, next slide, summary. Next slide, please. So this is our vision indeed on the rollout of this technology after the demonstration in the project. So we are busy with the first-of-a-kind plant localization and also the first engineering. Very important aspect to this is, of course, the licensing. So we have the partners NextChem and Stami Carbon in the project, and we are currently discussing the licensing with them. We have already agreed term sheets with them, and before the end of the project, we will also come to an agreement on the licensing. So after finishing this project, we will have the technology demonstrated, but also everything in place in order to start the first rollout to a first-of-a-kind plant. That's the vision. Next slide. I think this was the last slide. Yes. So with this, I would like to thank you for your attention, and I hope I gave you a good overview of where we are with the development of this carbon capture technology. Thank you very much.
Many thanks for your presentation. Of course, there will be time at the end to ask any questions. We now move on to our next speaker, following Eric's presentation. Dr. Sergey Martinov from UCL. Can you please, we are running over a bit, Sergey, so if you could please make sure that you don't do over more than 10 minutes. Is a double act by Sergey.
I'll try to do my best. Thank you very much for the introduction. Yes, yeah, it's this presentation, joint presentation by myself. I'm the one of the work package leaders on CO2 transport in C⁴U project. Together, I do this presentation with Thomas Cowley from the University of Sheffield, who was also involved in this work. CO2 transport is an important part of CCS chain, and well, it is important because it connects the capture plants with the those locations where CO2 needs to be stored or utilized. And in the project, we were developing some methods and tools that can become practically useful when it comes to CO2 transport solutions implementation, particularly in conjunction with the C⁴U capture technologies. Some insights about these tools and methods will be given to you in the next few minutes. Well, first of all, I'll do some brief overview, and Thomas Cowley will pick up on that. Next slide, please. CO2 transport, CO2 transport infrastructure is really can be really quite complex, and for many reasons. It is different to those infrastructures which already exist. It is non-existent at the moment at a large scale, would require collecting CO2 from many sources, transporting to various destinations, may involve different modalities of CO2 transport. And we also need to consider the hazards associated with CO2 itself, impurities that can be present, some uncertainties in the planning of the infrastructure, and some fluctuations and variabilities in CO2 streams that we may expect when we are transporting CO2. The practical implementation of CO2 transport infrastructure comes with certain challenges that need to meet the regulations, and also we would like to make sure that the design of such system is economic, efficient, and safe as well. So there are a number of targets when we are designing the such systems. For example, we want to ensure that the capacity of the system meets the requirements in terms of what is captured and what can be stored. We need to implement the suitable conditioning steps in the system. We want to make provisions for the flow assurance, avoiding two-phase flow, predict the physical properties of CO2 streams with the reliably and accurately, prevent dry ice formation, for example, in the system, or hydrates, and assess and manage the risks associated with the corrosion, material degradation, fracture propagation, and accidental releases. And that's how we come into place with the research on the CO2 transport in C⁴U project. And as I was saying, well, we have developed several practically useful methods and tools for the design operation of CO2 transport. Some examples are here. So next slide, please. The examples of our developments include, for example, developing methods for calculation of phase equilibria for CO2 carrying small amount of impurities, and we have derived very simple models using the Henry constant concept that can be implemented in the engineering process simulation tools for design of CO2 transport, also capture, conditioning steps, and potentially storage as well. We looked at the line packing in CO2 pipelines, and came up with the recommendations on CO2 line packing time and capacity calculations for CO2 streams in different phases. It can be gas phase, supercritical, or dense phase. We also applied multi-objective optimization methods to balance, for example, costs and environmental impacts, and other considerations can be included as well. For example, the time of deployment of CO2 transport solutions in industrial clusters. And the last thing on the list here, but not the least, well, it's the CO2 pipeline transport network planning. And this is the work that particularly was the focus of the attention by the University of Sheffield in the project, where they have developed the tools to optimize the capacity of the system, collecting CO2 from emitters in an industrial cluster or a region, then applying the agent-based modeling concepts to plan the capacity build-up and evolution of the network in the cluster. So the results of these studies were described in several deliverable reports and publications, and the list of these will appear in the chart. But at this point, I would like to pass over to Tom, please, and he will talk more about the tools that we're developing on their side. Over to you,
Hi. Yes, thank you, Sergey. Good afternoon, everyone. I'm Tom from the Brown Group at the University of Sheffield, working under Professor Solomon Brown. Today, I'm introducing something slightly different, and it's a tool we use to apply to the C⁴U project. So this is why I'm showcasing you, as well as I think it has application and value to many of the stakeholders in this call. So our multidisciplinary team brings together expertise in energy systems, spatially explicit modeling, and uncertainty quantification to solve some of the complex infrastructure challenges that I'm going to tell you about now. Next slide, please. So transitional infrastructure projects like the CCTUS projects face enormous financial exposure, and this is due to uncertain conditions. And as you see on this slide, projects like CCS must navigate multiple phases from concept to expansion, with significant uncertainties at each stage. So the key challenges in handling these uncertainties is what time will these additional sites connect? How much demand might they be adding to the network? And this has a knock-on effect to finding the least regret pipeline routes and sizes of the entire network, and finally predicting some of that stakeholder decision-making. McKinsey estimates that these unaddressed design risks represent 1.5 trillion in potential losses over the next 5 years. Next slide, please. So I'll give you an example looking at the National Grid's Humber Cluster project, which is connecting to the Endurance Aquifer out in the North Sea. Perfect example of what happens without proper planning tools. 6 years of iterative development with persistent redesigns due to the mismatches between the technical pipeline design and the actual industrial execution, so the supply chain. This led to delays and costs essentially, and that what I like to call the chicken and egg problem, which is this reiterative design problem that can incur expensive consultation costs and sort of absorbing a lot of information. And you get this sort of mismatch between the strategy and the technical design. Next slide, please. So this is where we think our software package comes in. It combines the network design, full holistic network design, with stakeholder behavior forecasting, so we can bridge the gap between the project's strategy and technical bottlenecks seen in the actual pipeline design. So as you can see, we can answer some critical questions for both the strategic planners and the technical design team. And the interface here allows us to run thousands of what-if scenarios. And this provides evidence to back decisions that might take engineering teams a huge amount of time. And essentially, I think of this as like a Monte Carlo simulation, but with more intelligence. So the agents have more intelligence, and we deploy these to see how the network grows over time. And we can run this over and over and over again. Next slide, please. So we validated this on the Humber Cluster project. I know this says hydrogen, but this figure actually is connecting up the high temperature industrial sites, assuming they will be decarbonizing with hydrogen. And that's why it says hydrogen on the slide. But importantly, we can distinguish between more certain routes and areas that are needing further analysis, like this challenging area you see highlighted on the map. This capability helps planners focus resources on highest areas of uncertainty rather than wasting time on sections with obvious design solutions. Next slide, please. Now to our work on the C⁴U project in the North Seaport cluster. Obviously, we aim to enable carbon capture from the steel industries, integrating it into this cluster. And we used the NE software package to build on the previous C⁴U work in predicting the possible CCS network sites that will join between 2030 and 2050, including up to 29 emitters by 2050. And this allows us to look at the total number of emitters when the emitters will join. If their joining is predetermined or arbitrary, if there's some decision making around that, offtake locations, expected emissions, etc., etc. This allows us to build case studies out, looking at as many future possible network scenarios as possible, and then we start to quantify those. Next slide, please. So using the NE software, we simulated the CCS cluster growth over time, revealing how it evolves. And this case study shows from 2030 with just 5 emitters, seen on the left, and on the right, 2050 with 29 emitters. Now, results from these studies will be presented at the European Symposium of Computer-Aided Process Engineering. And also there are papers to follow, so watch out for them. But essentially, we're ready to help organizations and projects minimize overbuilding costs by giving you evidence to make these least regret decisions and create infrastructure designs that can accommodate for the future growth and give you a bit more sort of evidence on why that might happen. Thank you for your attention. Please feel free to contact me if you think we could apply this to your project, and I welcome any questions. Thank you very much.
Thank you very much to Thomas and Sergey for their presentation on pipeline transportation work and these tools that have been developed in this area. This was the last presentation for today. Now we have the opportunity to for any questions from the floor, either on the chat messages or in person. So the floor is open to questions. There was, looking at the questions which were posted, one was on the carbon border adjustment mechanism and its impact on capture costs technologies development in the EU for the steel industry. And Dimitris posed that question. And Hannah, maybe you did provide a response. Is that any further comments on that from anyone?
There was a further comment around how CBAM can link to inflation and the societal acceptance of that inflation. I don't know, Vincent, if you want to comment on that.
Yes.
Sorry, I haven't seen that comment yet. I'll look into it and reply in the chat.
All right. Okay. So I don't see any. Okay, there is one question from Yasha. What are the environmental factors, impactors you consider for CO2 transport in multi-criteria decision methodology? I guess this would be a question to either to Sergey maybe or Thomas.
Yeah, that's right. Yes, yeah. Well, there are several impact factors that we have calculated using the life cycle analysis methods, and well, we had a university. Radboud University in the Netherlands, the partner who has helped us with this, and we grouped this into several categories: impact on the global warming potential, the environmental ecosystems, and impact on the yeah. Well, I think these were the main categories that we have included in the consideration, but well, there is a long list of environmental impacts that were predicted through the life cycle analysis.
Okay, thank you very much. There's another question: which software and database you use for the LCA? So again, this goes to our last presentation on CO2 transport. So,
right. Yes. Yeah. Again, well, this was the tool that developed at the university. In the Netherlands, Radboud University. Well, we have a publication based on that presented at the JHDT conference, and there was a link for that in the chat. Well, please feel free to download it. It is freely available to everybody. You can find the details there.
Any other points? In the meantime,
I can see that we have a participant that's raised their hand, Pratik
Yes.
Saha again.
Pratik,
I will
yes.
unmute them so they can pose a question if that's
Yes.
fine.
Over to you. I didn't see that. Thank you. Pratik. Maybe you could introduce yourself and your affiliation, Pratik, please. Over to you.
Yeah. Can you hear me, everybody?
Yes, we can.
Yeah, so I've got a couple of questions. The first is the different carbon capture technologies. We talked about the purity of the CO2. Is there going to be any NO2, any NOx, and any NOx, any SOx, and any oxygen in the mix? I think that's an important piece of information we need to know, especially when it comes to what we think would be a safe spec for pipeline transport. It'll be the same for ship transport as well. Just to give you some background, so I'm part of a CO2 spec task force, and we're doing some quite sort of significant R&D work on this, looking at the chemical reactions that may occur. And what we're seeing is that typical ship and pipeline transport conditions, if we have nitrogen dioxide, even at very small concentrations, we see sulfuric acid precipitation, which clearly is a significant corrosion risk to the infrastructure. And what we're seeing is that the transport environment, whether it's a reducing environment or an oxidizing environment, can have a significant impact on whether we form sulfuric acid. And then there's a question of the solubility limit of sulfuric acid in the CO2, which is also a function of temperature. How low does the temperature go? So that's an important area of research. And to close the loop, it'll be very useful to get information on the concentration level of these aforementioned contaminants in the CO2. So that's my first question. And the second question is for Erik van Dijk. The SVEX technology you mentioned, it looks interesting, of course, from the ammonia and urea production. But you didn't present a comparison with MEA on CapEx and OpEx, how that compares. I think that would be useful as well. Clearly, of course, the advantage of that technology is the side stream production of urea and ammonia as well. So that could offset. So I guess it would be useful to see if you have that option, how does it compare with MEA? And if you don't, how does it compare, kind of thing.
Okay, thank you very much. Two good questions over here. So I guess the first question regarding NO2 issues would be relevant maybe to Carlos and Gianpaolo. Either one of you would like to answer this? Maybe both. Carlos first.
Yeah, thank you, Harun. Well, in the case of the CASO technology, the presence of any nitrogen compound, especially when we refer to the enhanced CASO technology involving the extraction of the CO2 from the hot calcium carbonate by a pressure swing, can be ruled out. Basically, there is no known chemical compound evolving at these high temperatures to the gas phase or from the solids. When it comes to sulfur compounds, we have tested very limited at TRL7 the C⁴U. Unfortunately, this is work for the future, but from tests at lower TRL, we know again that even if you look at the equilibrium of calcium sulfate at these temperatures and in these environments, you can expect concentrations of SO2 SOx well below 1 ppm in the CO2 stream. Perhaps 100 ppb is more realistic. We are investigating if there are further kind of kinetic constraints for the generation of these gases. So one of the main claims, in summary, of the enhanced CASO technologies is the prospect to truly generate extremely high purity CO2, because when you look at both the capture step, taking place at high temperatures and creating these strong bonds with the calcium oxide, and the regeneration steps, the purity expected in the CO2 concentrated stream regarding the presence of these acid gases is going to be very, very high. Of course, more experiments are needed, but the prospects are very, very important and very, as I say, relevant to kind of justify the further development of the technology in this direction, because we are very aware that in the future, when comparing cost of capture technologies, people will want to put inside the box, inside the boundary of what is accounted for, to end up with a figure of CO2 capture, the purity issue. And as we know, I'm not an expert on CO2 purification, but we are very aware this is becoming a critical issue. Like costs tend to increase quite a lot, let's say, when you introduce as a boundary condition the necessary purity in the CO2 stream. So those technologies aiming at, let's say, competing in this technology market, we will have to demonstrate a kind of practical way out of this new problem, let's say, in the community.
Thank you, sir. Thank you, Collins. Gianpaolo, unless you have any further comments, quick, regarding NO2.
Yeah, very quickly. We are becoming more and more aware of this issue. We are now dealing with, so there is oxygen, surely in the gas treated by this place, there is certainly NOx in 100 ppm amount, something like this. So what we have been developing now is an overall optimization process which account for both capture and purification. Together with Sergei and UCL, we try to develop this analysis all together, because, as also Carlos anticipated, it's really an issue both from cost perspective as well from the safety and operation of the transport point of view. So we are dealing with this in the recent months. No preliminary results yet.
Thank you, Gianpaolo. Next question regarding the comparison of spec MEA. Eric, would you like to respond to that?
Yes, yes, sure. Yeah, I did not present this comparison because of time constraints, obviously. We have done this comparison by means of Techno-Economics and LCA. And we have also got some publications on that. So I would be happy to send you those if you contact the organization via an email or so. But to give you some indications, if you consider the energy used for CO2 capture with our C-REX technology compared to, for example, MEA capture systems, we are up to 2 times more efficient in energy. And that translates eventually roughly to a 25% lower cost of carbon avoided. That's the rough indications, the rough numbers. Of course, it depends on the case and on especially the prices for electricity and natural gas. So there's a whole range, but these are the rough numbers. So I'll be happy to share you some publications. Please contact me on that.
Thank you, Eric. Ines, I can't see any other questions on the chat unless I missed them. The floor is still open for any questions.
Yeah, so there's Fatih Bilek has to raise their hands. I see we're at time, so maybe if anything, we can give a quick answer for them.
Right, so who's the next question from?
Hello.
Yes, go on.
Can you hear me? Yeah.
Yes, we can. Over to you.
Yeah, I have a question for actually Carlos. Hi, Carlos.
Yes.
So it's a very interesting presentation on the chemical looping side, and then how actually chemical looping could be shifted to more producing different kind of revenue products. So can I just ask, what is your opinion of the chemical looping, general chemical looping technologies in terms of the size and how this could be miniaturized smaller scales?
Carlos?
Yes. Yeah, well, I can only refer to otherwise we wouldn't have time, to what we have done in this project. Like, you know, chemical looping is mainly, as a general technology, has been mainly developed for power plant applications so far, and using mainly circulating fluidized bed technology, yeah, moving the solids oxidized and reduced between different reactors. In this project, we took quite a different flow, yeah, and a different strategy, which is relying on these packed bed configurations where, okay, they come with many challenges, yeah, that I have no time to review, but many potential advantages, including some of the ones that you are pointing here. Like, okay, it can be a kind of more modular technology. Of course, you cannot go too low in a scale, because otherwise it becomes more and more difficult to maintain, let's say, high temperatures, adiabatic conditions, just with the energy flows and the thermal insulations typical for required for these systems. But basically, as I try to summarize from what we have learned in this project, I in my opinion now, I after 25 years working in circulating fluidized bed, calcium looping systems and other systems, I have fallen in love, let's say, with the packed bed technology that was developed much earlier for CIWEX and our colleagues here. Yeah, because it comes with a lot of inherent advantages if you can manage other issues, including the fact that you are not emitting powder. Basically, your gases are always kind of free of solids. When it comes to calcium oxide is a killer of any acid gas in the gas environment. Of course, you retain it in the solid, and eventually you will have to drop everything out and replace the material. But of course, we are talking about low-cost materials. And something very important I want to say, materials. To our surprise, yeah, the copper material, which is a commercial catalyst from Johnson Matthey that exists already in other applications, has behaved just truly wonderful in this testing. Yeah, honestly, reversible and non-stop cycling between oxidation and reducing conditions. And therefore, we don't, of course, there is always room to improve performances, to make them go quicker and better, these reactions. But the key message is, from the material perspective, from what we have, just mixing these commercial copper pellets and commercial mechanically suitable limestone material, we can go on, we have been able to go on at this relevant scale straight away from this project. So yeah, I can only be optimistic, but again, I guess I'm not very credible in this optimism. We need to keep demonstrating practically these new technologies.
Thank you very much. Any other questions? I don't seem to see raise of hands on my Zoom. Ines, can you help in case I missed any?
I believe it's all good at all. In fact, we're right in time, so
Right on
okay.
time. Okay.
Perfect timing.
All right. Well, I'd like to take this opportunity to thank all the speakers, all the people who have attended, especially to our panel members, given their busy time, to provide us with an excellent overview of the status of CCUS across the board. Edhard and Jeroen and Eric, thank you so much for your contributions to this presentation. And I would like to just conclude by directing sharing the C⁴U website for people. There is a lot of information on there about the C⁴U project. If you could please, maybe Ines, could you go to the C⁴U website and just share that with everyone, please? I will I think I can manage that now. Is that okay? Can everybody see that? Ines?
Yes, we can.
I've just shared the link on the chat, so perhaps everyone
Also
can peruse at their own will.
It's also available on the chat. So you'll find a whole host of information about all the work which has been done and the C⁴U project. And as I said, we are now in the last 2 weeks, 2 to 3 weeks of conclusion of the project. And as you can see on the website, you can find all sorts of information and also the newsletters and the deliverables and the achievements of the project. So there, and of course, if you have any further questions, you're always here to answer. So without further ado, thank you very much for the contributions of everyone to this presentations, to this forum. And of course, we have a major challenge in meeting the net zero emission targets, and I hope the C⁴U project is also going to be one of the important tools in meeting this final objective, urgent objective. Okay, everyone, thank you. Thank you for your time and efforts and contributions.